Hello, welcome back to my channel. This is a presentation on the history of the Lisp family of programming languages, from Lisp, its origins back in the 50s, all the way up to Racket. And for those of you who are more familiar with my channel, I do have a lot of videos on the Racket programming language. Basically, I think it's a great tool for learning programming languages, and I highly recommend anybody who's having a bit of an issue trying to become better at programming to really investigate Racket and the educational resources that are available around it, and to kind of overcome some of those blocks in terms of moving forward in your programming career. But I think a lot more people are becoming interested in the history of programming languages and computing, and looking back at how we got here and where a lot of these ideas came from. And so I thought it'd be interesting to give a brief overview of the history of Lisp. Now, given many reasons, including personal ones, I can't make this like a super in-depth presentation about all the history. I wish I could, but hopefully this inspires you to maybe do your own research and digging into what you find interesting about this history of this branch of programming. To start off with, one interesting thing about this is that the notion itself of computation is something that had to be invented, and it started out in the 1930s in earnest, about where people were really thinking about, oh, what does it mean to compute? And it was inspired by earlier work by Charles Babbage and other people around formalizing mathematics. But what came out of this was two main things. There's the notion of the Turing machine, which was invented by Alan Turing. Now, Alan Turing is called the father of computer science, and for good reason. The Turing machine was kind of the inspiration for how modern computer hardware works, as well as a whole class of languages that some people call imperative programming languages as well. But there's another bit of work that came out of this called the lambda calculus that was invented by a logician around the same time in the 30s, by Alonzo Church. And if you take a look at the lambda calculus and the Turing machine, they could not look more different in terms of how they're implemented. But later on, people did some work to prove that essentially that anything the lambda calculus can do, the Turing machine can do, and the other way around. So that they're very much equivalent. And not only that, but there's something called the Church-Turing thesis, which basically says these two models, being equivalent, are also what it means to compute. That anything that can be computed can be done in this set of either the Turing machine or the lambda calculus. So I'm not going to summarize the lambda calculus here. It's really interesting. It's actually fairly simple in terms of the amount of rules, but there's tons of nuances in how it works. But really, it's the idea where what we call higher order functions in programming came from. What a higher order function is that it's a function that can take in other functions as like parameters, and not only that, but return functions as well. In fact, that's exactly what the lambda calculus does. It continuously takes functions, applies functions, and returns functions. There's no real core values in there. And they actually, like I said, the real nuance around lambda calculus is how they deal with like primitives like numbers and so on and so forth. And so if you're aware with languages, when you ever hear people call, oh, well, you need to put a lambda there, where they're referring to an anonymous function, basically a function that doesn't have a name. That's why they're called lambdas, is because Alonzo Church decided to use a lambda as part of his notation. And if he had chosen another Greek letter, it would have been that instead. So here we are at Lisp, and here's the beginning. Lisp is one of the oldest programming languages. It was being developed right along Fortran in the 50s. And where it really started was at this AI lab at MIT, and when the notion of computing first started coming out and people were using some of these new computers, this lab was really interested in about what you could take away from human intelligence to make computers work better, and what you could use computers for to mimic human intelligence and learn more about human intelligence. The thing about it is that when I say AI, it's not AI as we see it now. Again, it was all about human intelligence and how it works. And AI really now is something completely different. Not only that, but the initial work of the AI labs was considered to be insanely ambitious. And a lot of people argue that basically none of it has come to actual fruition, that the gap between how we as humans work in terms of cognition and our brains work is so far away from how computers work that there's really no way that you could ever use the tool to gain insight. You ever use one to gain an insight on another at a fundamental level. And modern AI methods, some of them have actually, that's why the notion of when you hear people talk about machine learning, the machine learning came up as a tool to kind of separate itself away from AI, as in, artificial intelligence, what we can learn about intelligence, to, oh, how can we do certain types of things where machine, basically use certain algorithms to do things like statistical prediction to mimic the tasks that humans would do in terms of things like pattern matching or making decisions. And if you look at what's going on now, large language models, basically those are incredibly complicated statistical prediction machines. They have basically given a large set of inputs and tokens. They go on and predict the next token, which predicts the next token, and moves on. And of course, very complicated things around that. And it's an incredible amount of AI in terms of the, not AI, an incredible amount of computation in terms of the amount of parameters that are in the models, the amount of linear algebra you have to do, as well as, training and all the algorithms around that in terms of inference. But really, it is just statistical prediction. And the modern AI methods really bear little or no resemblance to this work here. The biggest example was at the AI labs at the very beginning. One of the things that they established that as part of doing an AI system, one of the things that it had to do is, like humans, it had to be go over and say, hey, tell me how you drew this conclusion or came to this result. And if you take a look at AI machine learning methods, increasingly as they become more complicated, it's almost impossible to say, oh, why did this thing spit out this given this prompt? Because of just the vast amount of the parameters there engaged. And you can't really get any insight that it can spit back on you and said, well, I did this because of this. And, some people have argued, well, that's not really as necessary. Some people would argue that's actually a critical part of intelligence is how can you trust the results when it can't explain to you why it did what it did? So just be aware of that the AI now, it just has nothing to do with what started at MIT in the 50s. So, but a lot of this work around Lisp came around wanting to do work around this idea. Lisp itself is kind of based on the notion of X expressions. So we already kind of knew that programming languages, and the reason they're calling them languages, is that they had syntax. And so you had things like Fortran that had its own syntax for doing numerical computations, making that easier. In Lisp, they made a choice to make as little syntax as possible and have the syntax for the data, the fundamental data that's using, which they call X expressions, to be it's the same as code itself. So you can't really tell. The only difference between an S expression that's being used as data and an expression that's used being as code is how you treat it. Do you evaluate it, or do you compute it? Excuse me, if you evaluate it or just use it as part of evaluation. So if you look at this, that's why you have all these parentheses bouncing around in X expressions. So here's basically the examples. Of course, you have these fundamental what they call atoms in Lisp, which are basically things like numbers, characters, symbols, so on and so forth. Booleans, obviously, an excellent example. And then you have two things. You have pairs, what is also called a dotted pair, which takes two X expressions and puts parentheses around them with a dot in the middle. And then you have a list, which is this, which is just an S expression with another X expression, and this around this. Now, if you take a look at this, it's one of those things where the parentheses don't constantly nest. There are shortcuts for fitting out a list where the syntax actually has S dot dot S, so you can have 1, 2, 3, 4, 5. But underneath it, it kind of treats it as if it was like nested. So just being aware that this is the fundamental underlying structure to S expressions. Also, because they were doing AI, there's a lot of this idea that they were interested in symbolic processing. And so Lisp had this notion of symbols. And symbols have never really caught on outside of this family of languages. Even though JavaScript, because of JavaScript was influenced by Scheme, has them, they're not really used. I would be surprised if a lot of very good JavaScript programmers knew that symbols even existed. And basically, there's basically with languages, what symbols are in Lisp, people would use with immutable strings and enums. So they just use a completely different set of ideas for them. But symbols are really not anything more fancy than what I said there. You can just treat them as an immutable string that is easy to compare to other symbols. When I was first doing this lecture, I was going over and trying to make sure I didn't miss anything, and I went over it 2 or 3 times, and lo and behold, the irony is one of the last things I forgot is that Lisp introduced the notion of garbage collection, which was the idea that you could find and remove unused memory, or basically references to memory that were no longer used, and remove them and compact your program so you didn't run out of memory, was invented in Lisp. And so that's why in Lisp you never see the notion of things like any type of memory management is kind of handled behind the scenes for you by the garbage collector. And so that was introduced in Lisp as well. One of the things also that was really influential that Lisp did in the very early is it introduced this notion of a read, evaluate, print loop. And what the read, evaluate, print loop was the idea that you can interact with the program or Lisp itself in an interpreted mode, what they would call, by typing in Lisp code into a teletype back then, which was literally a typewriter. That went kind of two ways. And it would be evaluated, and then the result would be printed back to you. And you could repeat this over and over again. And you can actually develop programs this way by ultimately creating these types of things. And then there's some functions that help you spill out the program if you wanted. And what's interesting is that this kind of notion of read, evaluate, print loop actually predates what we're used to in terms of what we think of as a shell in an operating system. And really what we think about as a shell, like bash in Unix or the command line proper PowerShell, is literally what kind of Lisp was in the terms of it's a language in which you can interact with and do certain types of things. It just happens to be a language in which there is a default set of syntax that makes it really easy to run programs in the OS. But if you've ever taken a look at a bash, it has its own programming language. With branches and all this other types of stuff. Same with the command programming language. The CMD has its own scripting language. There's there's people that like Bash and there's people that like C Shell scripting, but most people do Bash now in Linux. And, there's PowerShell and stuff like that. So, but this idea had to be someone had to invent it. And really, if you look back at it, it's the idea of Lisp itself. And this use of Lisp, you have to remember that when they were first doing it, it was basically, there was really not much of a notion of an OS. So the idea is when you just load up the Lisp interpreter and it would take care of everything. So it had all the hooks into the environment and it would be like the only program that you're running as you're doing stuff in. And as a part of this, again, I noted that the notion of program interpretation was also invented in Lisp. The idea that you didn't have to compile every program down to machine code for it to run, but you could have a program itself interpret it and do the work behind the scenes to do what you needed, was introduced by Lisp. And finally, Lisp itself allowed you to kind of work in a mixture mode where you could take a compiled Lisp program that had parts of it that were interpreted, where the interpreted parts were then basically interpreted and read back into the compiled environment and could be available to compile code after that. So that's really interesting. It's what people would refer to as self-modifying code in these days. And it's where the idea of things like a vowel in JavaScript came from. And it's, of course, nowadays very frowned upon for security reasons. And not only that, but it can really add to code complexity. But it's, again, it's like back then, there was not really a notion of security issues even being a thing. So this was more commonly used. So the notion behind Lisp is that, again, if you take a look at it, code looks like data, data is code. And they're really interchangeable. It's just how you view them and use them. It's not like other programming languages in which the fundamental data structures that you're using really have nothing to do with the syntax and how that's represented. You don't have to do things in Lisp that you have to do in other languages. If you want to treat a program and do stuff with it, you might have to parse it and do things like lexicon and parse it to make sure that it's correct. In Lisp, the fundamental tools that allow you to make a list make sure that you can create a correct Lisp program in terms of syntax. And because of this, it leads to the notion of meta-programming or programming about programming or code, basically treating code as data to another program. And that's a really useful idea in understanding programming languages because all the tools that we use to implement programming languages, from type checkers to compilers and all sorts of other tools, really come down to this fundamental understanding that, they treat that code as just an input into that environment. So the thing about it was really interesting is that what happened is that because of the symmetry between the data and code in Lisp, the REPL itself kind of fell out of people examining how to do things. If you take a look at the first version of the Lisp, the code to do the REPL is literally 6 lines. And it's a very elegant and almost brilliant set of code. Some have argued it's some of the most elegant code that's ever been written in terms of just how succinct but powerful it ended up being. And without this kind of symmetry of this code and data, it would have been really harder, much harder. And one would argue that the idea behind this REPL would have been delayed. And that might have delayed the need for having more interactive means of working with computers. Now, LISP was criticized a lot of people within MIT and others for not really focusing on performance, which is absolutely true. The AI people were really more interested in a little bit about doing the right thing in terms of correctness and understanding the program. But of course, some considerations had to be made because this hardware was, it's slow, and you had to do something to make sure it ran. And so there was some nods to optimization. One is that they made a very study choice of how to do the underlying S expressions as basically linked lists and make that really, really optimized for certain cases, and putting that on machines to make sure that worked really well. The other one was dynamic scoping, basically how you looked up variables and all that. And dynamic scoping is really weird. And I'll give you an example shortly of what I'm talking about. So this is some old school Lisp. So what I've done here is that I am defining a var called x, and I'm setting it to the value of 100. That's an atom. And now I'm defining a function called get-x. It doesn't take any parameters in, and all it does is return the value of x. Here I have a block that's a let block. And what a let block does is this is going to say, hey, in the scope of this thing here, everything in this expression, make x equal 1. All right. Now, if you're a programmer and you would look at this and look at the quiz question, and someone asked you, okay, what does this return? You would go off and say, aha, I'm very smart because I know about shadowing, and I know that this x always refers to this x. It doesn't matter. It's not this x that it refers to. Even though they have the same name, it's really that this x is bound up here, and this is a different type of x. And if I wanted to get to that, then I'd have to do something completely different. In Lisp, this returns 1. Doesn't return 100, it returns 1. And the reason being is dynamically scoping, what it does is it looks through the environment, and the first definition of that variable it sees, it uses. So I call getX, it goes off and says, well, I have this free variable here called x. I need to bind it to some value, or I can't do this anymore. So I'm going to look at the step up. Oh, look, there's a definition for x, and it's set to 1. I'm going to use that. Boom. Returns 1. And the reason they did this is that that's a very fast way of interpreting things. And not only that, in terms of compiling things, in terms of the call stack, it's actually really easy to do. So this is actually an optimization in terms of how you execute programs. So that being said, we know about modern programming, no programming language has ever worked this way. Almost all programming languages, and pretty much every programming language now is lexically scoped. The reason I say almost all is that in the early days of JavaScript, it had what was called function scoping, which was a little bit weird. But of course, even that was abandoned and depreciated in favor of lexical scoping. But as you can see, lexical scoping is hard because it has to kind of remember what X is referring to and just not do this fast lookup. Now, as a side effect of this, again, this is really fast, right? But it makes programmers now look back at Lisp and have the hardest time going, what is this actually doing? And why would you do this? And yes, it was really fast and easy to implement, but even more so, using dynamic scope can lead to really some very mind-bending code magic in terms of extensibility. And the reason being is that in Lisp, the dynamic scoping rules apply to where you look up a function. So if I'm calling a function getX, it doesn't refer to that in a lexical way either. It looks up through the environment and finds the first version of getX. And that can allow you to do all sorts of crazy stuff like, oh, I'll just completely override what these function means in this local context by putting a let around it, and then do some capturing stuff like that. So you can add hooks upon hooks. We basically recreate an entire environment with shadows and replaces all these other functions that would normally be called in the global space. Just all sorts of crazy stuff. The more you ponder it and what you could do with that, the weirder it gets. And so there's a book that talks a little bit about these really advanced usages. It's called Let Over Lambda. It's by Doug Hoyt. And it was kind of this celebration of all the stuff that Lisp did back in the day. The final thing that was added that Lisp kind of came up with was the notion of a macro. And what it came around to is they realized oh, well, you know what, this is, okay. We can't have everything in the language really be extended as a function. So, well, what if we have things that can't be a function, but we want to have this kind of extensibility? What could we do? And so what they realized is like, well, we know Lisp code is just data. So if we're doing things like running an interpreter or compiling things, why don't we have it so that we can say, oh, hey, when you see this bit of code that is a macro, instead of just trying to run it as the code as is, I want you to take it, evaluate it in this environment, right? And whatever it spits out, replace that where that macro lived. So basically it's literally like a substitution. Hey, instead of running this code and moving to the next step, run this macro, take what it spit out, put it back where that macro originally was, now run that and evaluate it, and then print it out. So this kind of allows you, basically what a macro does is it's run in the read stage or pre-eval stage, not at the evaluation stage. And this is C has a macro facility that was done way differently. It basically is just text replacement. But it's just, and if you look at other languages, there's more and more languages that have the concept of doing things at compile time. For example, C++ and templates. Rust has some compile time expressions, so on and so forth. So, but Lisp kind of invented that idea. And that also allows it to be really powerful because you can extend language in even more interesting ways than dynamic scoping would ever allow you to do. So as Lisp is moving forward in the 70s, it evolves into a set of dialects, each of them kind of targeting different types of things in terms of the machine that they're on or the environment they're in. One of my favorite is that there's a Lisp machine Lisp. And, basically it's one of those things where, what is that? But literally there's a thing that called the Lisp machine, which was hardware that was designed to run Lisp programs as effectively as possible. And there's some big demand for it in the 70s as Lisp was starting to get more traction. Now this is going on. There's also some pushback to create a kind of a common Lisp, which is basically, instead of having all these dialects that might diverge and never become compatible with each other, let's create a common ANSI standard version of the language. This first version of that work completes around 1980, and that ANSI standard committee still exists. It doesn't do very much because Lisp itself is fairly straightforward and solid. But at this time with Common Lisp, there's a lot of people that did do Common Lisp implementations. There's also variants being made. And in part 2, we're going to discuss one of those variants, which was Scheme, which was also made at MIT, but for completely different purposes. It was made for helping to teach a class. At the same time this goes on in the 70s and really coming up into the 80s, what happens is that what one of the people that was influential in the Lisp community, Richard Gabriel, calls the rise of worse is better. And what happens is at Bell Labs, they're doing a lot of research on their own. And one of the things that they release is this C programming language in Unix. And they're kind of tied together because Unix is a lot of C code with some assembly and all that kind of stuff, but it doesn't C. And if you take a look at C is almost really simple, almost kind of boringly so. It seems just to be like a light syntax over the underlying kind of modern architectures. It doesn't have a lot of library functions, so it certainly doesn't have, they do everything as very simple as possible. You have to do manual memory management, all these types of things. The type system is there, but it's pretty weak. But it's fairly easy to use by people that are understanding these machines, and it's really fast. Not only that, but the tools around it are really portable. The first C compilers, of course, were written in C, and very much bootstrapped themselves and to work well in these environments. And so they started working really, basically it was like, wow, these programs are really working very well. And it allowed Unix to get some traction because Unix was running on this like, oh, wow, you have this operating system that just isn't completely tied to this, bespoke version of an operating system that's running on on its own bespoke hardware. That's crazy. And the more the people that got into it, the more it started to get going. And then, of course, we know what happened is that the C programming in Unix, that overtook Lisp completely. And this notion of imperative programming, which wasn't new, we knew about it from Fortran and other languages before C, but it really takes the forefront and goes shooting off into the distance. You get C++, which kind of builds on top of that to give you a little bit more modularity and some interesting ideas around C, but still takes the speed of C++ because the first versions of C++ literally were just translated into C programs. And so you could just reuse the C compiler wherever it was. And Unix, of course, becomes a very much more popular operating system. And of course, today is amazingly popular. And so the thing about it is that in the paper, he talks about how what C does is in a lot of ways objectively worse than what tools like LISP and the Multics operating system did. And it's in terms of elegance. Basically, it has more power. It's, it doesn't have a lot of little shortcuts. What it does it extremely well. It's very elegant, and it's very easy. It's easier to reason about. There's not little traps. There's certain things that you don't have to do. Manual memory management, that's crazy. Why wouldn't you just do this? If you're going to do that, might as well write an assembly. But it's this lack of elegance traded for its own kind of practicality that makes it win. And the worst parts about it makes it better, makes it take over. And so it's why the C philosophy and the Unix philosophy really dominated the landscape, and has until now, I would say only until now, where we're talking about things like memory safety and security, where the C as the system programming language is kind of being questioned as becoming now much more of a liability than being an advantage. That a lot of the simplicity in C that they added in leads to, basically too much ability to do the wrong thing in terms of security, in terms of buffer overflows, memory flaws, all this types of stuff. And now we're seeing interest in things where there's languages that borrow from other programming languages and functional programming language ideas to create more safe or memory safe programming languages. Now, that being said, one of the things I'd like to point out here as a historical standpoint is I remember when Steve Jobs passed away. Obviously, a lot of people talking about all the great work that he did at Apple, and rightfully so, all these types of things. But the irony for me is that around the same time, or a little bit before, if I remember correctly, Dennis Ritchie passed away. And Dennis Ritchie was one of the key people for inventing C and Unix. And if you want to talk about someone who, in terms of tech influence, not from a market standpoint, but from a technical influence standpoint alone, Dennis Ritchie completely eclipsed Steve Jobs. It's not even funny. The amount of code that has been done in C and Unix, and the amount of code that lives on top of that, is truly enormous. It can't be understated about just how C is everywhere. And for a while there, it looks like Lisp would be one of the things that's what it was going to be. Lisp was going to be everywhere. And C really took over and displaced all that type of programming. So much so that the notion of functional programming, which is kind of the larger area for which Lisp lived in, really became almost niche. And the commercial uses of Lisp outside one or two very specific areas almost dwindled to nothing, and was replaced not only by C, but C++, later on Java, C#. And it wasn't until the early 2000s in which some of these functional programming ideas were actually being revisited. And I will probably do another talk about that later down the road. So there's this quote that's kind of adapted from Orwell, and it's, "Whoever does not understand Lisp well is doomed to reinvent it poorly." And if you're ever in the programming language community, this has been a spark of decades of discussion around, imperative versus functional programming, elegance in programming languages versus practicality. And for me, one of the things that would be fascinating is that it's also kind of an ongoing case study that we've kind of taken a look at. If you take a look at JavaScript and its history, JavaScript, it's kind of well known that it was inspired by Scheme, but also was fairly rushed because it was a demo at Netscape and wasn't really put together. And one of the reasons that he borrowed Scheme is that Scheme has a very short list of primitives that you can use, and so he was able to kind of cobble that together as a language much faster than something that was much more C-like. And of course, he borrowed some syntax from Java just because Java was, kind of an interesting. People were really kind of hip to Java at that time, and people like that syntax, C++ like syntax. So they kind of borrowed that, even though it has nothing to do with Java, and probably is one of the most confusing aspects of JavaScript today, is what it looks like versus what it actually is. Couldn't be more different, and so that's really interesting to see how that's played out and how it led to things like TypeScript on the one end, and only that on the other end for people kind of like saying, well, this was a very interesting experience and experiment, but the underlying environment in which it's created in terms of development is so uniformly convoluted and awful, we need to replace it. And I have some videos on my channel about what side I'm on this. I won't go into too much more detail there. Anyway, part 2 of this series will start by looking at Scheme. And if you made it this far, please like and subscribe. And I will see you in the next video.